Swayam Prabha. Digital India. Educated India.
Let's now solve a few problems based on the theory of residues and the argument principle that we discussed in this week. The first problem is computing an integral. We are going to do some calculus of real variables by using the techniques that we have developed just now. So, the first problem is to compute the integral from 0 to 2 pi of d theta by a plus cos theta, where a is greater than 1. So, at first glance this is a simple calculus problem and may not be a simple calculus problem, but at first glance this is a calculus problem, and the reason of solving this problem in this problem session is not straightforward. However, let us reduce this integral to an integral on the complex plane. So, to do that, let us look at the unit circle. Let gamma of t be equal to e to the power it for t in 0 to 2 pi. And on the unit circle, if z is equal to say e to the power I theta, then cos theta is equal to z plus z bar by 2. But we know that on the unit circle z bar is equal to 1 by z, so I will just write this as z plus 1 by z. So, the denominator, the cos theta, can be written as z plus 1 by z. When the right time comes, we will go back to that. And now let us write down our integral. It is 0 to 2 pi d theta by a plus cos theta. This is equal to integral 0 to 2 pi. Let me just introduce an e to the power I theta on the numerator and the denominator, and this is going to be a plus half of e to the power I theta plus 1 by e to the power I theta, which is z bar, the whole divided by, I will take the I out, and there is an e to the power I theta here. So, this is precisely rewriting by adding and multiplying and dividing certain terms. The idea is to write this as, maybe I should write that as well. This is just the integral from 0 to 2 pi of gamma prime t dt by a plus half of gamma of t plus 1 by gamma of t times gamma of t. And because of that, we can write this as integral over gamma dz by a plus half of z plus 1 by z times z. Till now, we have not done any major calculations. We have just done some minor changes of variable, changed the integral into a integral along a curve in the complex plane. Now, we have some really good tools with us to compute what happens to such integrals. So, let me just write down what this integral is going to be. This is basically, so 2 will go up here. Let me put a 2 by I times the integral of z square plus 2az plus 1. Now, let us focus on z square plus az plus 1. Z square plus 2az rather plus 1. This will have roots. I will just leave the checks to you at minus of a plus or minus square root of a square minus 1. These are going to be the roots, right? The 2's will cancel off, and this is what it will be. Notice that minus of a minus square root of a square minus 1, this will not belong to the closure of the unit disk, because a is greater than 1. Minus a minus square root of a square minus 1 will be less than minus 1. So, the absolute value will be certainly greater than 1. And if you look at minus of a plus square root of a square minus 1, just say that I'll leave it to you to check that this is going to be between -1 and 0. Simple checks will tell you that this is what is going to happen. So now if you go up and look at the function 1 by z square plus 2az plus 1, this is a meromorphic function with singularities at minus a plus square root of a square minus 1 and minus a minus square root of a square minus 1, and the in C minus 0, right? And by the residue theorem, what we will be able to conclude is that 1 by 2 pi I times the integral over gamma dz by z square plus 2az plus 1. If you look at this particular integral, this is going to be equal to w gamma of what is the first point? Minus a minus square root of a square minus 1 times the residue of f at the point minus a minus square root of a square minus 1 plus w gamma of minus a plus square root of a square minus 1 residue of the function f at minus of a plus square root of a square minus 1. We just noted that the point minus a minus square root of a square minus 1 does not belong to d bar, and therefore the winding number is going to be 0. That's something which you should sit down and check, and therefore the first term is going to vanish. So this is just going to be equal to the winding number of gamma around minus of a plus square root of a square minus 1, which is equal to 1. We have done the necessary prerequisites to conclude that this winding number is 1. Gamma, remember, is the unit circle, and therefore this is going to be the residue of the function f, and the point at which we are looking at the residue is exactly this. To compute the residue, let's consider the function 1 by z square plus 2az plus 1. By writing them as partial fractions, this is just going to be equal to 1 by minus of a plus square root of a square minus 1 minus of a minus square root of a square minus 1 times 1 by z minus, so this big bracket, minus of a plus square root of a square minus 1 minus 1 by z minus minus of a minus square root of a square minus 1. Right. So now if you look at the residue of this function, the residue of this function is going to be the residue of this function, and notice that the function given here is going to be a function holomorphic on the unit disk, because minus a minus square root of a square minus 1 is holomorphic on the unit disk, and what contributes is exactly this. Therefore, this is equal to, let me just write down the expression here. This is minus of a minus this, so this is going to be 1 by 2 times square root of a square minus 1 into 1 by z minus of a plus square root of a square minus 1 plus a function h of z, which is holomorphic on the unit disk. We are not worried about it. There will be a power series expansion there, and therefore, hence the residue of 1 by z square plus 2az plus 1 at the point minus of a plus square root of a square minus 1, this is exactly going to be equal to the coefficient, which is 1 by 2 times square root of a square minus 1. So we now know that if you look at this integral, that is equal to 1 by 2 times square root of a square minus 1. Right? That's precisely what we have computed. But then what did we want to compute? We wanted to compute 2 by I times this. So hence 2 by I times the integral over gamma dz by z square plus 2az plus 1 is equal to, well, we'll multiply by 2 pi I and divide it. This is going to be 1 by 2 pi I times the integral of dz by z square plus 2az plus 1 which is now equal to 4 pi by this. This is going to be equal to 4 or rather pi by 2 pi by square root of a square minus 1. If you notice, it is remarkable that a purely calculus problem was reduced to a problem on the complex plane, and the theory of residues was used to compute the answer. Let's solve one more problem in a similar vein. Let's look at real integral which needs to be computed. So, we will compute the integral 0 to infinity of 1 by 1 plus x square the whole square dx. Again, at first sight, this might not look like it has anything to do with residues and argument principles, but we will somehow bring in the story of residues into this picture again, and we'll see how it works out. As is to be expected, 0 to infinity of 1 by 1 plus x square the whole square dx. This is equal to half times the integral from minus infinity to infinity of 1 by 1 plus x square the whole square dx. Being an even function, this certainly holds, and which now is the limit as r goes to infinity of half of integral from minus r to r 1 by 1 plus x square the whole square dx. Let's now consider the function. Consider the function f of z to be 1 by 1 plus z square the whole square. There is nothing surprising with the function, it's just the function from above that we are interested in. And notice that this is just z plus I the whole square into z minus I the whole square. Z square plus 1 can be written as z plus I into z minus I, and this is precisely what we are interested in, right? And if you now draw the picture, the poles of this particular function are at I and at minus I. Let's consider the following curve that I am going to draw from r to r, minus r to r, along this straight line in this direction, and then go along the semicircle. So, consider the curve gamma to be the curve gamma minus r to r concatenated with gamma, let me call the curve C to be gamma minus r to r concatenated with gamma, where gamma of t is just capital R e to the power I t for t from 0 to pi. So, notice that the curve is just whatever is being drawn in the green, going this way, and then we are coming along this direction. That is precisely what our curve C is trying to do. And if you look at the integral of 1 by 1 plus z square the whole square dz over the curve C, again 1 by 2 pi I will come in here. This is just going to be equal to the winding number of this curve around the point I, and the winding number of this curve around minus I is going to be 0. We will be able to conclude that this is equal to 1 times the residue of 1 by 1 plus z square the whole square at the point I. This is precisely what it is. Let's just quickly compute what the residue is. That's a very easy computation to do. So, 1 by 1 plus z square the whole square is actually 1 by 1 let me see, z minus I the whole square into 1 by z plus I the whole square. Now, if you consider the power series expansion of 1 by z plus I the whole square, so suppose 1 by z plus I the whole square is equal to some summation b n z minus I the whole n. This is a holomorphic function in a neighborhood of I, and therefore this certainly makes sense to write it like this. Then 1 by z minus I the whole square is just going to be equal to, or rather let me put it this way, the Laurent series expansion of 1 by z square the whole square is just going to be equal to b0 by z minus I the whole square plus b1 by z minus I plus a holomorphic function. And therefore, the residue is going to be equal, residue of 1 by 1 plus z square the whole square at the point I is just going to be equal to b1. But we know what b1 is. b1 is the coefficient appearing in the power series expansion of f around I, right? And therefore, power series expansion of what? Of this particular function. And hence, d1 is just going to be equal to d by dz of 1 by z plus I the whole square evaluated at z is equal to I. The power series expansion is around I after. If you sit down and do the computations, this is going to be equal to 1 by 4I. We have, let me write down what we have, 1 by 2 pi I times the integral of C of 1 by 1 plus z square the whole square dz is equal to 1 by 4I. That is good because this integral to the left, this is nothing but the integral of gamma from minus r to r of 1 by 1 plus z square the whole square dz plus 1 by 2 pi I times the integral gamma 1 plus z square 1 by 1 plus z square the whole square dz. The first thing to note is that this is again equal to 1 by 2 pi I times the integral from minus r to r 1 by 1 plus x square the whole square dx plus the same, and it is the limit 2 pi I times the limit of the thing on the first term as r goes to infinity that we are interested in. Let us look at the second term 1 by 2 pi I integral over gamma 1 by 1 plus z square the whole square dz. Suppose this is I, then the absolute value of I is just going to be less than or equal to 2 pi r by 2 pi times. So notice that f of z is equal to 1 by 1 plus z square the whole square. Now if you notice 1 plus z square, absolute value of this is greater than r square minus 1 by using the triangle inequality, and therefore 1 by 1 plus z square whole square absolute value is going to be less than 1 by r square minus 1 the whole square, which is r to the power 4 minus 2r square plus 1. And therefore, if you impose this bound over there, absolute value of I is going to be less than or equal to 1 by by dividing by r, we will be able to get r to the power 3 minus 2 times r plus 1 by r. And the limit as r goes to 0, this goes to 0. Or rather, limit as r goes to infinity, this goes to 0. And therefore, the second term does not contribute anything. This term hence vanishes as the limit as r goes to 0 is taken. Therefore, what we have is the following. Hence, taking the limit as r goes to infinity, we have 1 by 2 pi I times the integral minus infinity to infinity of dx by 1 plus x square the whole square is equal to 1 by 4I, and hence what we get to conclude is that half of integral from minus infinity to infinity of dx by 1 plus x square the whole square, this is equal to, the i's will cancel off, the 2 will cancel off, this is going to be equal to pi by 4. So a seemingly difficult integral to compute is being computed by using the power of residues, and we get a concrete answer. In fact, we can slightly modify this problem and compute the integral when we have an e to the power ix, for example, lurking at the top from say minus infinity to infinity. If this is the problem, we have already done all that is needed to be done to solve this as well, because now what will happen is that again we have to just make the premise perfect. So this is the curve from minus r to r followed by the curve here. Again the points of interest to us will be I and minus I, and therefore if you look at e to the power ix by 1 plus x square the whole square, rather if f of z is being taken to be equal to e to the power iz by 1 plus z square the whole square, this is going to be 1 by 1 minus rather z minus I the whole square times e to the power iz by z plus I the whole square. And therefore, the residue of f at the point I is just going to be equal to d by dz of e to the power iz by z plus I the whole square, evaluated at z is equal to I, which I have done the computation already. This is going to be equal to minus of I by 2. I have done the computations. You should sit down and integrate and evaluate and see that this is exactly what we will be getting. So the argument here about why this is the residue is exactly the same as earlier. It's going to be the second term in the power series expansion of e to the power iz by z plus I the whole square around z is equal to I, and that is computed by looking at this derivative evaluated at I by using our knowledge from power series. So we have been using quite a lot of theory we have developed so far to conclude this, and now the limit as r goes to infinity of integral minus r to r. So that's going to be what we are interested in, ix by 1 plus x square the whole square dx. This is what it is. This is going to be the integral from, this is going to be equal to 1 by 2 pi I is going to come in here, 2 pi I times minus of I by 2e, and we get this is equal to pi by e. So I have rushed through this particular problem to obtain a solution. However, the idea is that it can still be broken up into these two curves with an e to the power iz featuring at the top, and the second term here that will converge to 0 as r goes to 0, as r goes to infinity in an exact same manner as it happened in the previous problem. And the first term is what we are interested in, that is going to be exactly equal to pi by e. Let me conclude this problem session by an application of the Roche's theorem along with many other things. Of course, let me write down the problem and then we will see. Let omega be some open set which contains the unit disk. Let omega be an open set which contains the closure of the unit disk, rather containing d bar. D bar is the closure of the unit disk, and let f be holomorphic on omega. So we take a function which is holomorphic on omega, which satisfies the condition that f of absolute value of f of z is equal to 1 whenever absolute value of z is equal to 1. So the unit circle is being preserved. Unit circle is getting mapped to the unit circle. Then prove that, so f be a non-constant. Let me impose that extra condition, holomorphic function on omega. So now the problem is to show that then the disk is contained in f of omega. Of course, if it was a constant holomorphic function, this wouldn't be true. That is the reason why I had to impose the extra condition of non-constant. Okay, so let's see a solution. The solution is going to have multiple observations. The first observation is that f should necessarily have a 0 in the unit disk. So, claim there exists z in D such that f of z is equal to 0. So, what will happen if that is not the case? If not, then g of z equal to 1 by f of z is holomorphic on D, right, in fact on D bar. So, let me say there exists this on D bar. We know what f is on unit circle. So, we know that f does not vanish there, but we can now say that it is holomorphic in a neighborhood of D bar. It is holomorphic in some u which contains D bar. Now, by the maximum principle, we have absolute value of f of z is less than or equal to 1 for all z in the unit disk. Because it is less than or equal to 1, the absolute value is less than or equal to 1 on the unit circle. Everywhere in the interior, the absolute value is less than or equal to 1. Now, let us look at g. Absolute value of g of z is equal to 1 whenever mod z is equal to 1. Yet again, we are using the fact that g of z is equal to 1 by f of z and mod f of z is equal to 1 whenever mod z is equal to 1. And by a very similar argument, as above, by using the maximum principle on g, we have absolute value of g of z is less than or equal to 1 on D for all z in unit disk. But that implies that absolute value of f of z is greater than or equal to 1 on D, because f of z is exactly equal to 1 by g of z, or rather g of z is equal to 1 by f of z. Yeah, both are true. And therefore, we now have from star and star star, let me call this star star and let us call this star. We get to conclude that absolute value of f of z is equal to 1 on D, in fact on D bar, in particular on D. But what do we know about a holomorphic function which is non-constant? Because it is a non-constant holomorphic function, the image of D under f is going to be an open set by the open mapping theorem. F of D is open, and hence absolute value of f of z is equal to 1 on D is a contradiction. Should sit down and think about why it is a contradiction. If it is an open set, it cannot be sitting inside the unit circle in R2, and therefore, so I will leave that to you, and therefore, hence our assumption was wrong. There exists z in D such that f of z is equal to 0. So, what we have established is that there exists some z in D bar. In fact, z in D, we know that it is not going to be on the unit circle. So, there is a z in D such that f of z is equal to 0. So, we used the maximum principle and the open mapping theorem to conclude this. Of course, we still have not concluded that every w is going to be in the image. So, in particular, let us pick now some w in the unit disk. Define g of z to be equal to minus w, the constant function on omega, right. In particular, what do we know? We know that absolute value of g of z, which is equal to w, which is strictly less than 1, is less than the absolute value of f of z. We also know that f does not vanish on the unit circle. Now, by Roche's theorem, maybe I should put a minus w, that is much better. Now, by Roche's theorem, f and f plus g have the same number of zeros with equal multiplicity, have equal number of zeros in D counted with multiplicity. Why is this the case? What is the curve that we used from Roche's theorem? The curve here is the very simple unit circle, and because we have the unit circle, the interior of this unit circle is going to, it's null homotopic in omega because d bar is contained in omega, and D is going to be the interior of our unit circle. So, the number of zeros in D counted with multiplicity of both f and f plus g are going to be the same. We know that f vanishes on D by our previous claim. Claim was that there exists some z such that f of z is equal to 0, and hence by Roche, hence there exists some z in D such that g of z is equal to 0, or rather f plus g of z is equal to 0. Roche's theorem said, oh, I think I made a mistake, equal number of zeros counted, it's not correct, it's not wrong. F and f plus g is what I have written. So, f plus g will turn out to be equal to 0. But what is f plus g of z? F plus g of z is just f of z plus g of z, which is minus w, which implies that f of z is equal to w. And that tells us that because the choice of w was arbitrary in our unit circle, D is contained in f of omega, and that is precisely what we were trying to prove. So, Roche's theorem along with the maximum modulus principle and open mapping theorem is used to conclude that the unit disk is contained in the image.